Thanks so much for coming. This is the first eminent chemistry lecture. What's an eminent chemistry lecture? We have hundreds of lectures in this department. What makes this one special is it's being given by an eminent member of our department. Very excited about that. We're going to have one of these a quarter. All right, this is the one for fall quarter, obviously. In spring quarter, February 28th, which is a Friday.
That's winter quarter.
Sorry?
That's winter quarter.
Winter quarter. February 28th, the speaker is going to be Iwan Andrioche. Is Iwan here? There he is.
He's right here. He just walked in.
So he is going to be our eminent chemistry lecturer for winter quarter, and then for spring quarter, it's going to be Chris Vanderwall. Okay. Now, the other thing that makes this special is that we've got this great reception over in that side too, 1201. So after the lecture, everyone is invited to go over there. Please brave the rain. It's only about a 2-minute walk. Right? Please come on over and have some wine and beer and food. Okay, I'll try and remind you at the end of the seminar. So this seminar was really the brainchild of Andy. So he's going to introduce our first eminent chemistry lecture.
Oh, that was good. You threw me right under the bus, didn't you, Greg? Okay, so it is really my pleasure to welcome you all to this seminar this afternoon. So I think there's a brochure or a poster about Bill's background, so I'm only going to briefly say that he grew up in Wisconsin. For reasons that I'm not exactly sure, I guess, in a town that no one needs to know. He got his formal training at the University of Wisconsin, where not only did he major in chemistry, but he was a coxswain for the crew team, a word I've never used in public. And I hope I never ever use it. He then went to UCLA, where he worked with Fred Hawthorne, and then he went to Cornell, where he worked with Earl Mutis to get his to complete his training as a synthetic inorganic chemist. He then started his career at the University of Chicago, and UCI was lucky enough to learn here more years than I'll mention. And in that time, Bill has done, I think it's safe to say, a remarkable job in developing a research program that is somewhat unusual. And I was trying to think how to put this in perspective for not only the visitors from the outside, but for my colleagues. So I have a prop, and I'm somewhat hesitant to use this, but I think it hopefully will be apt. This is a common household item, at least I hope for most of you. What I want to try to do is to try to show you in 2013 how inorganic chemistry is somewhat divided, and then how Bill's research program has impacted the field of inorganic chemistry. I think many in the audience know what organic chemistry is, for the most part, and many know what physical chemistry is, and even theoretical chemistry. Oh, of course they do. Okay, so the prop I'm going to use is not meant to indicate anything about the area of inorganic chemistry or Bill's research. It is, for you analytical types in the audience, it's a pie chart. It's just my way of using the pie chart. Okay. And I want you to know that I planned to practice this today, but one of my colleagues said, don't use this, Andy. I'm going to try this and see how it goes. So inorganic chemistry that we know today in 2013 really started about 120 years ago. It was founded by a guy named Alfred Werner, and 2013 is an important time because it's the 100th anniversary of him winning the Nobel Prize. And he founded what is called coordination chemistry. It took inorganic chemistry from the domain of physical chemists and metallurgists, and it looked at metal ions and how you could take ionic forms of metal and manipulate them into discrete molecules. And so, okay, this might not work. So today, coordination chemistry is a dominant form of inorganic chemistry. And let's say that the percentage is about these many tissues. So we'll leave that here. There's another area that is equally dominant in inorganic chemistry, and it's called organometallic chemistry. Oh, I should say that in the coordination chemistry realm, the chemistry department is well represented with outstanding people. Haydek's lab, Jenny Yang's lab, my lab we all do coordination chemistry. So organometallic chemistry, that's really the study of metal-carbon bonds, and they're used in catalysis for the most part. And again, UCI is well represented. I guess this is not exactly what you want to think. So, the Blum lab, the Jarvo lab, the Dong lab, the Haydek lab again is dominated by, use that organometallic chemistry. Then there are the material scientists. They dominate an area called solid-state inorganic chemistry. It's been on for years and years and years. It's gone from looking at just solid-state structure to actually taking that structure and using it for new materials for important purposes. Heterogeneous catalysis, making new things for energy science. And again, oops, that's physical chemistry. We're great at that. Matt Law's lab, Shane Ardo's lab, these are the people that use this, and this is a big area. Okay. Now, there's one more area. It's called bioinorganic chemistry. It's a study of metals in biological systems. Your proteins that are working in your body right now, they contain metal ions. A third of them contain metal ions. As you breathe, you're using a metal ion to bind dioxygen in your lungs and transferring it around. And we are, again, well represented in bioinorganic chemistry in this university. The Ribby lab, the Poulos lab, my lab does this. Okay, so here we are, bioinorganic chemistry. Marcus, this is for you. Here's some other stuff you don't worry about. This is the other stuff. So here we are. Here we are. This is the use of, and you know, I forgot something very important. All of these tissues use metal ions that are in the transition metal series. Those are the 30 elements that sort of connect the periodic table. And this is what dominates inorganic chemistry. And I would say if you went to any inorganic department in any university in the United States, almost everybody would be working on transition metal ions in some capacity. There's a whole realm, we don't have a periodic table here, there's a whole realm of metal ions that are ignored by most inorganic chemists, and I'd say more than most, 98 to 99%. Those are the rare earths. That's what's represented here. And the reason, well, there's twofold. If you want to use these metal ions in molecular systems, it's really difficult. If you want to put organic compounds to bind to them, technically it's incredibly difficult to study these. So that's the first thing. And the second thing is the dogma in the inorganic community, these are boring compounds. That these rare earth metal ions don't do anything that would be of consequence or importance in inorganic chemistry. We're fortunate at UCI to have the leading lab that has proven that incorrect. So of all these small number of tissues, don't think of it as that it's unimportant or it's a niche science. It's an overlooked science. But not very much anymore, and that is pretty much because of the Evans lab. And I would argue that in the last 15 or 20 years, not all, but most of the major advances in molecular rare earth chemistry and looking at reactivity of these types of compounds have come from Reines Hall, second floor, from the Evans lab. And what you're going to see today are examples of those types of things, how you can take these small molecules and you can activate other molecules like N2 or NO in ways that we hadn't thought of. You can look at discovering new types of oxidation levels that had never been thought you could make. So this discovery-based science is now leading the way in this new area, well, semi-new area of inorganic chemistry. And you can tell because when you look at some of the young people that are starting out their careers in inorganic chemistry at other universities, They are following the role that was started by the Evans Lab. And so these small sheets represent a significant contribution. And so with that, Bill, you got a lot of toilet paper? What that really means? Well, welcome.
Thank you. So you just got the show. Now you have to listen to the seminar. Thank you, Andy. I'm a little short on time here, so I'm going to go fast. First of all, I'm from Menominee Falls, Wisconsin, and you should hear that at least once in your life. And I wasn't a coxswain, I was a stroke, which is a big difference. And Matt will appreciate that, but you won't. And I'll explain it to you sometime when you're older, okay? So let me begin by thanking Reg for the invitation to speak at this lecture series. We go all around the world and talk about our science, but we don't come home and give a full lecture to our colleagues and our coworkers and our students very often. And I think it's a really good idea to do this, and I'm honored that you asked me to give this first one. And I won't hold it against you that you asked Andy to introduce me. So I'm going to talk to you this afternoon about discovery at UCI and discoveries that happened in my laboratory. I'm going to tell you about a string of discoveries that I never thought would happen. I never thought I would be giving this lecture here at UCI. And as I tell you about these discoveries and the details from my laboratory, what I want you really to think about is discovery in your area of science or your area in general. And maybe there are some lessons that can be learned from what I tell you about the discoveries in our laboratory that can help you make discoveries in your area of endeavor. Now I'm going to tell this story in a little strange way. I'm going to use this title, The Importance of Questioning Scientific Assumptions. That's a very strange title for a seminar on science, because as scientists we know we should question scientific assumptions. It's part of the scientific method. And my first slide is a little bit unusual in that it just reiterates this issue about questioning assumptions and shows we've been doing it for hundreds of years. So here's a quote from Descartes, a 17th century mathematician: "Do not acknowledge as true anything that is not obvious. Do not assume anything is true that is not obvious." Here's one from Michael Faraday, 19th century chemist, warned against the tendency of the mind to rest on an assumption and when it appears to fit in with other knowledge. And this slide gives me an opportunity to introduce a couple of my favorite books that I would recommend to all the young investigators in the room, as well as the more experienced investigators like Andy, for example. These talk a lot about discovery and coming up with ideas and questioning assumptions. And I wish I'd read those books when I was a young investigator. I recommend them to all of you. So let me just bring this up to date with a quote from the late Rick Smalley, who discovered buckyballs, one of the co-discoverers. Main thing you need to learn is doubt. Don't believe anything you're told without good reason and judgment and argument. So we've been saying question assumptions for hundreds of years. Why am I talking about that today? We know we should do it, but we don't. We don't do it enough. And the point of my lecture is to get you all thinking about questioning assumptions. I'm going to show you this afternoon how much new chemistry we found by pushing through some assumptions in my area that I was certain were true. And these assumptions are not narrowly defined esoteric assumptions. They're very basic. One involves one of the two most common types of chemical reactions, specifically redox reactions and specifically reduction reactions. Another one involves one of the fundamental aspects of metal-containing molecules, namely what constitutes a stable metal-ligand bond and a stable metal-ligand bond distance. So I'm going to talk about assumptions that were very basic in my area of science that I'd studied for many years, and I was sure I knew the rules in this area, and I was totally wrong. And as I go through the details of my chemistry and explain how we push through those assumptions and the consequences, what I really want you to do is be thinking about how that applies to your area of endeavor. And so the purpose of my talk is to encourage you to think about questioning assumptions in your area. Now, to do this properly, I need to give you some background on F-element chemistry. And as I do that, I'm going to come back to this slide. As I do that, I'm going to show you how we had to push through assumptions just to be able to work in this area. And in this Advice to a Young Investigator, the author makes the point that when you're starting out as an independent researcher, you want to show the establishment you can do something new, and so you tend to push through assumptions. But this is something we need to do all the time on all of the aspects of the science that we're working on. So, thanks, Reg. When I started working with the F-elements, this was a typical periodic table of that time. And this periodic table was in the conference room of my senior inorganic colleague at the University of Chicago. This was his periodic table. And it's mounted above a chalkboard. And you look for the F-elements, they're down at the bottom of the table. And what's happened is somebody's rolled the bottom of the periodic table underneath here to get a few extra inches of chalkboard space. And Ev knows this colleague was short, so he didn't even need that chalkboard space. But this was the view of the periodic table at that time. And so I'm going to tell you about these elements. I want to give you some definitions. These are called the lanthanides. We'll also talk about uranium and thorium a little bit. Scandium and yttrium are grouped with these, and they're called collectively the rare earth elements. And they behave a lot like the lanthanides, and yttrium, which we'll talk about a lot today, is the same size as holmium, behaves like holmium a lot, and I'll show you reasons for that in a minute. But early on, people weren't interested in the lanthanides, and one of the reasons is that these elements have a trivial name as the rare earths, and that suggests they're not very common, and they're probably expensive, and why would you want to work with them? And that assumption is just not correct. As I fill in the blanks here, the early lanthanides are comparable to cobalt and lead, and even the least common thulium is more common than silver, mercury, and gold. So they're not rare, they're not that expensive compared to these elements. That's not a reason to avoid working with them. A better description of why people weren't interested is in a quote from a very large, comprehensive organometallic textbook in which they say, we're not going to talk about these elements. So this is in the introduction, and they say some nice things. First, they say that these elements are ionic and oxophilic, and they're large, and they do some nice insertion reactions. But their bottom line is that these elements lack the variable oxidation states, the back bonding ability, and the orbital extension, which are crucial to reactivity of real metals, of transition metals. So I'm going to show you why they said this. We're going to talk about oxidation states, and we're going to talk about orbitals, and we'll talk about orbitals first. So the lanthanides are unusual in the periodic table in that their valence orbitals, their action orbitals, and electrons do not have very great radial extension away from the nucleus. In fact, it doesn't go beyond the extension of the electrons that are part of the xenon core of the configuration of every lanthanide. Lanthanides are 4Fn. And so the typical picture of an F orbital, you don't study that much in school because it's buried inside this core. It doesn't interact with the outside world. And that's very different from all the other elements in the periodic table. The transition metals, for example, have their d orbitals that stick out and form covalent bonds and activate interesting substrates and do catalysis. So these are much more ionic, and they look much more limited for that reason. So if we look at the early rules of how you make a lanthanide compound, they're quite simple. The first one is you forget about orbitals. The limited radial extension of the orbitals, valence orbitals, results in minimal orbital effects. So it doesn't matter how many F electrons you have. And the atoms are all quite similar. The elements are similar from one to another because these are buried in the core. Oh boy. I'm having trouble with this, sorry. Oh. Yeah. As I said, these are much more ionic, and so they're going to interact with ligands like halides and oxides, not as interesting as carbon monoxide and alkenes that you might want to do in catalysis. The ligand geometries aren't specified by any electronic effects. Whatever you can get to optimize electrostatics will be good enough. And so if electronics aren't very important, what becomes very important are steric factors. And so this looks very primitive, very simplistic. When I wrote my first NSF proposal, it was rejected, and they said, why don't you work in some other part of the periodic table where there was some chance of doing some interesting chemistry? But if you take these rules and you put them together and you think about the fact that the F configuration is not important and steric factors are important, and you put that together with the lanthanide contraction, this gradually decreasing radial size as you go across the series, you have a basis for a very nice way of precisely tuning reactivity. So if you have a reaction that's controlled sterically, you always can change the ligands around the metal to affect that. But with lanthanides, you can not only change the ligands, but within a given ligand set, you can change the metal with all of these 14 or 15 possibilities. And we include yttrium here down with holmium because it's the same size here, and it behaves very much like these elements. Okay, so that allows you a lot of chance to size optimize. There's no other set of metals in the periodic table where you have so many chemically similar elements that have a gradually changing radial size. And I just want to show you one example of that size optimization because it'll be important later in the talk. So here's an example from our laboratory where we made some lanthanide hydrides by hydrogenolysis. It turned out people had put hydrogen on all the elements in the periodic table except the lanthanides, and so we ended up making the first lanthanide hydrides. This is probably a 4-center reaction, a sigma bond metathesis for my Chem 216 students. We'll talk about that on Monday. And what happens when we do this reaction with erbium under these conditions, we get a 50% yield in 24 hours. But when we change the size of the metal by just a couple hundredths of an angstrom, we shut that reaction down. So this is a very dramatic example of how changing the size of the metal can have a big implication in the reactivity in the system. That size optimization is very important. Okay, so that's the orbital part. Let me address the oxidation state part of that introductory paragraph. So the +3 oxidation state is the most stable for all the lanthanides, regardless of the number of valence electrons, because these aren't very important, remember. When I started in this area, there were a few other oxidation states available, but not many. Cerium 4 and 3 +2 oxidation states. And none of these had a 4 and a 2 with the same metal, so they all were 1 electron redox coupled. So you couldn't do the 2 electron oxidative addition, reductive elimination that's so important in transition metal chemistry. So this looked very limited. I didn't disagree with any of the facts I just showed you, but when we started out in this area, we said, yes, the lanthanides are different, but that doesn't mean they're bad, and maybe that difference is a basis for unique chemistry. And that's what's driven our research at UCI all these years, looking for something unique. We were doing exploratory synthesis. That's something that's very hard to get funded for these days. We wanted to make new molecules and see what they would do. That's very nebulous as a target, but that's what we did. And we decided we would start out looking at reductive chemistry, and we looked at the 3 +2 ions that nature had given us. We picked the most reactive of these, samarium, and we made the first soluble metallocenes of samarium-2, a solvated one and a surprisingly bent unsolvated one. And these molecules were wonderful and essentially established the first part of my career. And I just want to show you a couple examples to show you the importance of reduction chemistry in this area. So here's an example with the solvated decamethyl samaracene reacting with an olefin and carbon monoxide to insert 2 carbon monoxides into what was the CC bond, double bond. So we've done a double homologation to make a bisenolate. That's not a common reaction in organic chemistry. It's done with a lanthanide, which is not supposed to interact with these soft ligands like alkenes and carbon monoxide. So that's just one example. When we went for the unsolvated decamethyl samaracene, we were able to make the first dinitrogen complex of an F element. And nobody expected that was possible because these were too ionic to interact with dinitrogen. But more importantly, this was the first dinitrogen complex that had two metals coplanar with the dinitrogen. In all the decades of work on dinitrogen, if you had one metal interacting with the pi bond in this plane, the other metal would come in perpendicular. So this was a new type of dinitrogen bonding, and it was found by doing the lanthanide chemistry. So we got a lot of good chemistry out of samarium. We call it the good samarium in our lab. But it has some drawbacks. One is that the +3 products are paramagnetic, so we can't get all the information we'd like from NMR spectroscopy. And the other thing is we can't do this size optimization that I talked about. We're stuck here. And these are both very different in their redox properties, so we only have one metal. We can't do size optimization. Now, if you'd asked me some years ago, what are you going to do, Bill, in the future in terms of reduction chemistry with these elements, I would say, this is what nature has given us. We'll change the ligands, the conditions, the substrates, but this is what nature has given us. This is how you do reduction chemistry with the lanthanides. And that assumption that that was the limit of redox chemistry with the lanthanides was completely wrong. And what I'm going to do for the rest of the talk is show you examples of other ways of doing this reduction chemistry that were always there and were just waiting to be discovered, but people were so focused that for 90 years these were the only ions that were available. That's all they thought about. We discovered a number of new ways of doing this redox chemistry, more ways than I have time to tell you this afternoon. So I'm only going to tell you about a couple to be illustrative and then show you where that's taken us. So the first one starts here. We were looking at redox chemistry of decamethylsamaracine. We thought it was strong enough to reduce cyclooctatetrene. That likes to be a dianion. That would require two of these metallocines. That could give us some structure like this that looked very crowded, and we thought it might be interesting and might have interesting chemistry. So the reaction occurs. We get reduction, but we don't get a bimetallic complex. We get a monometallic complex. So we get this little piece. And what's left over is this metallocene cation and this anion. And the surprising thing is that these two pieces come together to make what was the first molecule in which there were three of these pentamethyl cyclopentadienyl rings around one metal. And that was a surprise because it had been in the literature for a long time that you can only put two of these large rings around even the larger metals of the periodic table, uranium and thorium. And everybody believed that. And they believed that because the cone angle of this pentamethyl cyclopentadienyl ligand was 142. So you can't put three of those around one point till you'll exceed 360. But somehow, just by mixing these, we suddenly changed the cone angle of this ligand. So now it's 120 degrees. These form just on mixing. So how do you change the cone angle of the ligand? Well, one way you can do it is to move it further away. And indeed, that's what happened in this compound. If we look at typical samarium pentamethyl cyclopentadienyl distances, and you compare them with the ones in this molecule, the ones in this tris Cp star, as we call it, are all about 1/10 of an angstrom longer than anything we'd ever seen. Now, if I went to Andy and said, Andy, next week we're going to make a molecule in which all metal ligand bonds, all 15 metal carbon bonds are going to be longer than anybody's ever seen by 1/10 of an angstrom. That's the difference between a single and a double bond. That's a big difference. If I told him that, he'd say, Bill, you need to see a psychiatrist and get a little help. You're pushing a little too hard. But here it is. It's a molecule with all the bonds longer than we'd ever seen. Better than that, associated with those long bonds is reactivity. So normally these rings are inert ancillary ligands. They don't do anything. And this has all kinds of reactions that I'm not going to tell you about. Some of them go about through this A-to-1 intermediate, but I want to focus on the reduction. Those long distances make this a reducing agent. We can get an electron out of it, and it behaves very much like a +2 system. We get the same cation, we get an electron. The difference is that the reduction is coming from the ligand, and it's giving us a Cp star radical that forms a dimer, and we get this as a byproduct. So this was really very interesting to me because now we're doing redox sterically controlled. Usually you change redox electronically, not sterically. And so we call this sterically induced reduction. And it's not as powerful as samarium-2 reduction. So I showed you this could reduce nitrogen. This will not reduce nitrogen, but it'll reduce cyclooctatetrene. That's a reasonable reduction reaction. And we were excited about this because if we can do it with samarium and if we could make other tris cyclopentanediol lanthanides, then we could get this size optimization of the reduction chemistry that we never could do. We wouldn't be stuck right at samarium. So I'm going to talk about that. That's what would allow us to do these kinds of reactions with all of these metals, and that would be an advance for us. We made the early metals. They're larger, less crowded, and I'm going to talk in a minute about how we tried to go down and make smaller and smaller, more crowded systems. But first I want to talk a little bit about applying the sterically induced reduction to uranium. So this compound had been made in 1982, but no one ever thought about taking this uranium hydride plus tetramethylfulvene to make a CP star because they didn't think this molecule could exist. So you can make that molecule. It's crowded enough to do this sterically induced reduction reaction, but it also is a uranium-3 complex. So it has some redox chemistry there, and if you put those two together, we have an unusual situation in which we have a uranium-3 compound that will do 2-electron reduction but give us a uranium-4 product. So that's kind of unusual. So we reacted this with cyclooctatetrene, 2-electron reductant with a molecule that likes to be reduced by 2 electrons. And it gave us kind of a mixed result. We had to change the stoichiometry to get a clean reaction. But eventually we did, and indeed it had 3 cyclooctatetranes that got reduced. And that meant this was a 6-electron reduction. And it was done by just 2 of these ligands. So that meant they're not 2-electron reductants, they're 3-electron reductants. We're getting 1 electron from uranium-3 to uranium-4, and then 2 of these ligands are acting as reducing agents because our product only has 1 CP star per metal there. So when we double that up, that's where we get the 6 electrons. Turns out when you react this with azobenzene, you can reduce this to a bisamido complex. That's a 4-electron reduction. And so this compound will deliver 4 electrons, 1 from sterically induced reduction and 1 from the uranium-3 to uranium-6. So it can be a 3-electron reductant, a 4-electron reductant. It also can be a 2-electron reductant in the reaction with chlorobenzene. And I want to show you this one because it goes stepwise. And it gave us a chance to see which of these processes would go first, the sterically induced reduction or the uranium-3. So if sterically induced reduction goes first and makes this intermediate with 1 equivalent of chlorobenzene, then we would expect to get something that's still uranium-3, but we've lost 1 of the rings, and here's the chloride byproduct. So that's a known compound, so that made a lot of sense. If uranium-3 reduction occurred first, we would make a uranium-4 product. We'd still have all the rings, and if the chloride was here, we'd have this molecule, which looks impossibly crowded because it has 3 of these rings. That's very crowded already, and then another one. Well, you know what the answer is because you know how I'm telling this story. We assumed it was this one, and it was just the opposite. So uranium-3 reduction occurs first, and in fact, we can make molecules that not only have 3 CP stars, but they have another ligand on them as well. And then this uranium-4 complex will do reduction and give us a uranium-4 product by sterically induced reduction. Once we realized we could make this molecule, we came up with about 4 other syntheses of that molecule. And we now have about 19 different reactions that will give us molecules with 3 CP stars and at least 3 CP stars and often another ligand. 19 different reactions that any F element lab around the world could have tried. Retrospectively, they all look quite reasonable. But nobody ever tried any of those reactions because the belief was so strong that you couldn't put 3 of these big CP stars around a metal.
Did you do those because it's UCI?
Yes. Very good, Evan. So I want to come back here to the lanthanides. We wanted to go all the way down to the smallest lanthanide because it's diamagnetic, and yttrium's diamagnetic, so these are good ones. And as you get smaller, you get more crowded, you get more reactive. And the yttrium was difficult. We made it by the tetramethylfulvene method, but we had to make it in cyclohexane because if we made it in benzene, we ended up with a phenyl complex. So it turns out these rings are so crowded that they'll take a hydrogen from benzene and make a stronger acid as a product. So a fairly unusual reaction. When we tried to make the lutetium complex the same way we made the yttrium one, we got this CH activation again. And in fact, we didn't make the molecule. We got CH activation of both of the components here. And so we ended up metallating the tetramethylfulvene and making a vinyl, and metallating one of the methyl rings here and making this tuckover complex. So that raised some questions that led to the second way of doing reduction that I'm going to tell you about. So we had this very crowded molecule with lots of redox and CH activation reactivity. If you go to the tetramethyl analog, I'll call this CP tet, this is CP star. If you go to the tetramethyl analog, it has none of these high reactivities. It's not crowded, it doesn't do anything special. And you can make the CP tet lutetium, and we weren't able to make this one. And we wondered, very simple question, where's the crossover point between normal reactivity and high reactivity? Is it at, so we know it's not at 12 methyls, is it at 13 or 14? And how close can we get to this one? Can we have a mixed ligand system and have more reactivity? So we set out to make these mixed ligand complexes. We knew how to do that by displacing a tetraphenyl borate from this metallocene with one type of ligand. We add another type of ligand. We got a very nice result out of this. We got a new type of binding of cyclopentadienide. So it turns out this is trihapto, but usually when you have a trihapto cyclopentadienide, it's 3 ring carbons. We have 2 carbons, 2 ring carbons, and 1 external one. Okay? So that was a new type of binding for cyclopentadienide, which is a very old ligand, so we're happy about that. This is the synthesis of the 2-to-1, 2 CP stars to 1 CP tet, and we wanted to do all of them, and so another one was 1-to-2, and that one just wasn't crystallizing for us. And Tom Miller was working on this project, and he was about to get married, so he set up a whole bunch of crystallizations, and he went off and got married and went on his honeymoon. And when he came back, he got this product. And this is a reduced nitrogen compound, like I showed you before. So N2 has been reduced by 2 electrons. We see some CP tet dimer in the byproducts, and so it looks like the CP tet anion is doing the reduction, and this would be like the sterically induced reduction I just showed you about with the different anion. But remember, I told you that these tris CP star compounds did not reduce nitrogen. So something even more crowded than this one does not reduce nitrogen. Okay? And we would think if there was any ligand in this molecule that was going to reduce nitrogen, it wouldn't be the CP tet, it would be the CP star, the pentamethyl, that's more electron rich. So I thought Tom was just still high from his honeymoon, and he just switched vials and he didn't know what he was talking about. I said, you have to make the N15 labeled version because nobody will believe you, including me. And he did. He was able to make this. And then he looked at all the variations of the mixed species, and he ended up with this series of reactions. The smallest metal lutetium with the largest ligand set is not reactive. So the most crowded is not reactive. The largest metal with the smallest ligand set is not reactive. So the most crowded and the least crowded are not reactive, and somehow the in-between ones are. Okay? And the problem was this reaction took 3 weeks, the time that he took for his honeymoon, which I thought was... No. Anyway. If he hadn't taken that long a honeymoon, we never would have discovered this chemistry. We tried everything, and Megan Fieser got involved with this, trying to speed up this reaction. We tried every conceivable way we could think about. And eventually, we tried photolysis. And much to our amazement, this photolysis changed the reaction time from weeks to hours, and even allowed us to get this one to do the reduction. Now, we never tried photolysis because there's no lanthanide-based photochemistry. The lanthanides have their f orbitals buried in the core. The transitions are not very strong. They don't have intense absorptions, and so there is no photochemistry. We never would have thought that photochemistry would work in this system. So we focused on this one in our interactions with the FERCA group to try to understand what's going on here. And it turns out in these mixed ligand systems, the highest occupied molecular orbital has a lot of electron density on that CP tet ligand that is the one that's lost. And the LUMO looks a lot like a DZ squared. That's okay. That makes a lot of sense. If you look at the systems that are not mixed ligands, the so-called homoleptic, where all the ligands are the same, the picture of the homos is very different. The electron density is spread out over all 3 rings, not just 1 ring. If you look at the UV visible spectra of these systems, They have two humps here, which can be modeled by theory, but they're very different from the homoleptic, which only has one. And it turns out that this extra band is the one that's photoactive. Megan showed that. And the calculations then from the Furka group gave us some reasons to expect why this reaction might happen. So there's a couple transitions from some occupied orbitals that are heavily located on the CP-TET ligands to go up to this LUMO. And if that happens, this is going to reduce electron density here. It can come off as a radical and dimerize, which we observe. That would leave us with something that's formally yttrium plus 2, an oxidation state that hadn't been observed, and that would be strong enough to do the reduction. So photochemistry is another way of doing redox with these elements. The third way, I'm going to come back to this slide that I showed you before. So for 90 years, we had these 3 plus 2 ions. And then in 1997 to 2000, sort of a miracle happened in my view at UCI. We ended up doubling the number of plus 2 ions. I mean, if you think about doubling the number of plus 2 ions in any area of chemistry, or of any oxidation state, that's just amazing. And this was done by a collaboration with Mikhail Botchkarev in Russia. And he had developed ways to take the metal and the iodine to rack them directly in the absence of solvent so that you could make these molecules. Nobody thought you could make these molecules in solution because their calculated redox potentials were so negative that everybody thought they would decompose the solvent. So Botchkarev found a way to make them without solvent, and then we found ways to crystallize them with solvents that were not decomposed by these diiodides, and we got the 3 new oxidation states. And we wondered why nobody had discovered these before, and we found out the reason is that they readily reduce nitrogen. So if you take these new divalent iodides with any ligand, an amide, an aryl oxide, a cyclopentadienide, before you know it, their intense color has faded, and you've made a plus 3 complex. The plus 2 has gone to plus 3, and you end up reducing nitrogen. So people had seen this decomposition, but they never knew what they were making. They never knew they were making these dinitrogen compounds. And presumably this is forming through some intermediate that's so reactive that we can't isolate it. So I show you this again, the iodide plus the amide to presumably make this and reduce nitrogen. We wanted to study these complexes, but these iodides are made from the metal and iodine in the melt at 500 degrees in a quartz furnace that George Meyer built for us, so not an easy reaction. And we wondered if we could make them an easier way from these plus 3 amides just by reducing them with potassium. So those amides had been made in the 70s. They were much easier to make, and indeed you can do this. And this is kind of a scary situation to me because these guys in 1973 could have discovered all the chemistry that I talked to you about with dinitrogen back in the 70s if they just tried to make the 3 most likely plus 2 ions that could be made. But they believed so much that you couldn't make those in solutions that they didn't try this very simple reaction. Okay, so I'm showing you this again. Presumably we're reducing the trivalent to this plus 2 intermediate, and that's doing the reduction. But when we did these reactions, we expected this plus 2 intermediate to be intensely colored. And we didn't see that. And so we wondered if this was really going through this pathway. And so we decided to try this with yttrium. And I had to work hard to convince my student to do this because he was convinced it wasn't going to work. But much to our amazement, we can reduce nitrogen this way with yttrium, even though it doesn't have a plus 2 state. And it works with holmium as well. And then we went to erbium. This shouldn't work at all because potassium has a redox potential of minus 2.9. This is more negative. This calculated potential is more negative. But it works with erbium. It works with all of them, as it turns out. And we have a new way of doing plus 2 redox chemistry. Just taking a plus 3 ion and an alkali metal that'll deliver minus 1 plus 3 minus 1 equals plus 2. But we're doing plus 2 chemistry without any plus 2 ions. And so when we wrote this paper, we wrote if these reactions proceed through this, this is the first evidence for these ions. But I never believed those ions would exist or could exist. About the same time, Mike Lappert in Sussex was doing reactions of this type also, and he started in 97, and it took him to 2008 to get some evidence for a plus 2 complex. He argued that lanthanum at the beginning of the series, the 5Ds and the 4Fs are similar in energy, and so this was a 5D1. And interestingly, this molecule didn't reduce nitrogen. So it seemed very different from the chemistry I just showed you, and we didn't think there was a connection. Anyway, that was another way, third way of doing divalent reduction chemistry, the LNA3M method. And I'll just show you one more, and then I'll stop on this topic. If you look at these nitrogen compounds, they're also reductants. And I'm just going to show you a couple examples because they involve reducing carbon oxide. So we can reduce carbon dioxide to oxalate, make a carbon-carbon bond. That's not the normal way that carbon dioxide gets reduced. And this is being done by the nitrogen 2- ion in these systems. And we also can reduce carbon monoxide. This is much more complicated. It's a dimer. We'll just look at this half. Here's the half reaction. We can take 3 carbon monoxides with 2 electrons, and we make a carboxylic acid derivative of ketene, a carboxylic acid derivative of ketene. We've made 2 carbon-carbon bonds, and this carbon is completely freed from oxygen. We've completely broken the carbon-oxygen triple bond. And so again, this is done with the nitrogen in these molecules and gives us a fourth way of getting this +2 reaction chemistry. Okay, so you're thinking now, I've shown you a lot of ways of doing F-element chemistry. Who cares except us F-element chemists? What I'll do for the rest of the talk is try to show you how this can be useful. So I showed you this reaction before, the amide with a reductant reduces nitrogen into 2-. We published this in JACS. We had a good crystal structure, good yield, NMR, everything was fine. We thought that was the end of the reaction. But there's more going on in this reaction. We subsequently found that that sample that gives us a good NMR spectrum, if we put it in Andy Borovik's EPR spectrometer, we get an EPR signal. So there's something diamagnetic and something paramagnetic in there. And when we track those down, we got molecules that looked a lot like this, except in the crystal lattice, there was an extra potassium. So that meant there had to be an extra negative here if there's an extra positive here. And we could make a couple versions of that. And these species had longer NN bonds than we had in the N2-2-. They weren't as long as a single NN bond, which would be equivalent to an N2-4-. And so it was very tempting to fill in the blank here and say we had N2-3-. But nobody had ever observed that ion in all the decades of work on dinitrogen fixation. We had some comfort looking at the oxygen analogs because there is an analog to N2-3- in the oxygen series. It's superoxide. And you can even get a crystal structure of superoxide. So it wasn't so crazy that we had a crystal structure of this N2-3-. But what held us up on publishing this is we were so worried that maybe this was really the known N2-4- with a proton that we couldn't see by crystallography. And so we really had this. And it took some EPR work again with the Borovik lab to show that in fact we had the first example of N2-3-. And I won't go into the details of this triplet of triplets with the 2 spin-1/2 yttriums and the 2 spin-1/2 nitrogens, but it's definitive for that species. And the Furka lab then explained why or how we got this radical, or maybe why it's stable. The unpaired electron density is in an orbital that's orthogonal to the metal orbitals. It's protected by the ligands here. And we're in this system where there's not a lot of interaction between the metal and the ligand. So there's not a lot of communication with the outside world for this unpaired electron to say, hey, I need some partner to pair up. And so maybe that's why the lanthanides allowed us for the first time to get N2-3-. So we had this radical, and we thought, well, we'll react it with another radical, NO, and see if we get some interesting coupling. And we got a molecule that looks a lot like this N2-2-. And we thought, well, that N2-3- is a pretty good reductant. And we're making an N2-2- and we're reducing NO to NO1-. That would make a lot of sense. But the NN distance in this molecule was a little bit long compared to what we would expect for an N2-2-. And we started thinking about it, realized that by crystallography, we can't tell if this is NN or NO. Can't tell N and O apart at this level. And so if that's an NO2-, for charge balance, it has to be 2-, and that's an oxidation state that had, again, never been observed for nitric oxides. The bond distances make sense that it's more reduced. It has a longer bond distance. And if we look at superoxide and what's been called supernitride here, it turns out that this NO2 minus fits right in. And so, again, the EPR was used to identify this definitively as the first example of NO2 minus. And the orbital picture looks the same. So all this redox chemistry gave us two new oxidation states of two of the heaviest studied diatomic molecules that chemists look at, that nobody's seen before because perhaps they hadn't been using these metals. Then we got another bonus. It turns out that this N2,3- ion is very good at coupling paramagnetic lanthanides to make single molecule magnets. So dysprosium has a high magnetic moment, and when we made this molecule, it turned out it's a single molecule magnet. And I'm just going to blow this up to show you how these work. So paramagnetic systems, normally, this is a magnetic field versus the magnetization of the sample. If you start with a normal paramagnetic system, you can turn on the field and you'll magnetize it. You turn off the field, it loses its magnetization. You can polarize it north, you can polarize it south, back and forth. But a magnet, when you magnetize it by increasing the field, and then you take the field away and go back to field 0, it stays magnetic, stays magnetized. That's a characteristic of a magnet. And in fact, you have to put the field in the opposite direction to get it back to 0 magnetization, and then you can magnetize it in the other direction, turn off the field, it stays magnetized. So this is like a little switch, an on-off switch that you can do magnetically, but it's being done with a molecule, the smallest magnet you could possibly make. And so single molecule magnets have been studied by people for 20 years because they offer interesting options in information storage and miniaturization of all kinds of devices. But the problem with them is that the highest operating temperature in those 20 years of research was 4 Kelvin. When we got this compound, we were delighted to see that it doubled the operating temperature of what people had found the last 20 years. And it was using these lanthanides that in a different way than people had used before. And then we went to terbium, which is not supposed to be as good as dysprosium because its total angular momentum is smaller, and it turned out to be even better, and we almost doubled again the operating temperature. So that's another bonus that came out of this reduction chemistry. So I just want to finish by coming back to this slide and these strange reactions where we might have this +2 in the reaction. It took us a long time, but eventually we found some conditions in which we could do a reduction in the absence of nitrogen at low temperature and observe something that suggested we were making a +2 ion. So this is an EPR that's split to a doublet by the yttrium, suggestive of yttrium +2. But despite all our efforts, we couldn't get any crystallographic information on that, and we don't want to claim a new oxidation state without a crystal structure. When we went to this cyclopentadienyl system, we got what we were looking for. We got, again, the intense color characteristic of these ions, EPR spectrum, and this one crystallized and gave us the crystal structure of the first yttrium-2 complex. So we have 3 anions here, cation here, so by difference this is yttrium-2. This is located near the ring, but it doesn't affect these distances. They're all similar. All these rings are similar. So we're excited we had a new oxidation state, another new oxidation state. We were surprised when we compared the metal ring centroid distance for the +2 to the +3 because the +2 is only a little bit larger. And in all of our experience with +2 samarium, ytterbium, and europium, we typically would see much larger distances between +3 and +2. Here's 1/1500ths of an angstrom. This was a little strange to me, but then we thought about the fact that this is really a transition metal. It's not a lanthanide, and we're looking at a D system, not an F-based system. And for transition metals, changing an oxidation state doesn't change the distances very much. So that's very characteristic of a D system. This is what we'd expect for an F system. So we had the yttrium. We thought we'd do the same reaction with holmium. And it gives almost the same result. Same type of crystal, isomorphous with the yttrium. And again, now very strange, a small difference in the +2 and the +3 distances. Not what we would expect for an F system. And now I'm going to show you the erbium, and it looks exactly the same. So we made the first yttrium-2, the first holmium-2, the first erbium-2. And it looks kind of trivial now because it's all the same reaction. But I just want to point out that these are all done in ether. It has to be ether, not THF. And they're done at low temperature. And the person that made these, Matt McDonald, worked very hard to do this. And I just want to show you how that works. He had to do everything at low temperature. So he put his starting materials here, cooled them down, transferred in some cold solvent. That generates the intense color here. This is a frit that we're going to tip upside down so we can do the filtration at low temperature and take the filtrate into that flask. So this goes upside down. We pull a vacuum over here. That'll pull the solution over. We detach the filter part, remove the solvent, get some crystallization solvent in there, and he's able to make these. Took him a day to do each reaction. Very, very difficult. He got tired of doing that, and he came up with this reaction system that's really quite ingenious. This whole thing's about 6 inches, and it's designed to fit in the refrigerator of our glove box. So he takes all the equipment and he puts it in the refrigerator of the glove box. He takes it out and he quickly runs the reaction. He doesn't have to do all that other stuff that I showed you in the other slides. And if he gets the concentration of his starting materials just right, and he pushes it through this column of potassium graphite, we call this a flash reduction column. If he pushes it through at just the right rate, the reaction is complete here, the graphite stays here in the frit, and this is so concentrated that as these drops start to come out and evaporate, they start to crystallize and the crystals fall in the bottom of the flask. So very ingenious. If you want to see it live, he's got a YouTube on this, and if you Google that, you'll get to him. So once Matt had a better way of doing this, he started looking at more. These three had very similar bond distances. I told you they also have very similar colors. And their UV visible spectrum was similar. And that's strange. This is a transition metal. These are lanthanides. We again went with the Furke group to get some understanding here. And here's the highest occupied molecular orbital for the homoleptic one. This looks like one of the other orbitals I showed you earlier. And here's the LUMO. Here's where you would expect the electron that you would add to yttrium-3 to go. And indeed, when you look at the HOMO of the yttrium-2 complex, it looks very much like a DZ squared orbital, as if you'd put an electron in here in that product. So that all makes sense. What surprised us, because yttrium's a D system, what surprised us was that the holmium looks exactly the same. And so this suggested that when we add an electron to F10 holmium, we're not making an F11 system, we're making an F10 D1. That's electron configuration we've never seen in F element chemistry. Just I don't know how to think about it. And so we now have this situation where with the traditional lanthanides, the first 6 that were discovered, the way you get the divalent is you add an electron to the trivalent and it goes into the F orbital, F6 to F7, 13 to 14, etc. And now suddenly we're seeing something different, like the electron goes into a d orbital. The d orbitals are supposed to be high in energy compared to the 4f. So why would you put one in a high energy orbital when you had empty 4f's down here? So Matt went on with his studies and looked at some other lanthanides. Here's one that has a redox potential minus 3.7. This should definitely not happen. And again, he was able to get crystals and get the first terbium-2 complex. This one was different in that the cation was not near the cyclopentadienyls. It actually formed a sandwich with a ring here. And that told us we didn't need to use potassium 18 crown 6 all the time for these reactions. And so that led Matt to try a different sequestering agent for the potassium, a cryptan. And that allowed him to work at room temperature in THF if he did it very fast, just less than 5 minutes. And with that, he was able to make a new series of +2 complexes with the potassium on the, held by the cryptan. So he did the yttrium, the holmium, the erbium, the terbium I just showed you, and then he went and finished the series. He got praseodymium, he got gadolinium, that has a reduction potential minus 3.9, and lutetium, he got them all. And so now we have all the +2 ions for all the lanthanides. That's very exciting to me, but even more exciting is they may have this 5D4FN configuration. And this may explain why these calculated redox potentials don't match up with the reaction chemistry we're observing, that potassium can do this reduction. These were calculated assuming that the electron would go into an f orbital, and perhaps it's going into a d orbital. This mixed configuration has a lot of consequences in magnetism that I'll mention in just a minute, but I want to show you that this is the periodic table when I started. In 1997-2000 we added a few, but now we have them all. We don't have promethium because it's radioactive. But we have the opportunity to do this size optimization. It was always there. All of these ions were always there waiting to be discovered, but nobody did the reduction reactions to try to make them. And I'm not going to talk about the magnetism, but we don't really know how to think about the magnetic moment of a mixed configuration like this. But it's conceivable that it could have a magnetic moment higher than any metal that we've ever seen before. But we have to get that data before we can make that claim. Okay, one more little bit. What about uranium-2? We had these new lanthanide +2 ions. And we said, well, uranium is different. Uranium can be +3 and +4 and +5 and +6. Probably not the same. And so we just didn't think about doing it. But in fact, it works just like the other systems. The starting material was known in 1986, but nobody evidently tried to reduce it. But here's the first uranium 2+ complex. And here it is again. When we made this complex, we thought the referees aren't going to believe it because they're going to say there's a hydride here that we can't see by crystallography, and it's really uranium-3 hydride and not uranium-2. So we made the uranium-3 hydride to show that it was an independent compound. We can make it from the uranium-3 precursor, and we can make it from the uranium-2 and hydrogen. It's a different compound. That's definitely the first uranium-2 complex that's known. So let me just conclude about what I've told you today. For a large part of my career, this is how we thought we had to do divalent reduction chemistry. It's the only thing that was available. That's what nature gave us. And what I'm trying to show you is that there's many other ways to do that reduction. So I showed you the sterically induced reduction with these molecules that weren't supposed to exist. They exist, and they do reduction chemistry. I showed you that we could do photolysis, something that's not normally done with the lanthanides. We discovered those 3 ions. That led us to this type of redox system. The nitrogen products of this redox system are reducing agents. Here's a whole series of things I didn't tell you about. You can be happy about that. The N2,3- and the NO2- are good reductants. We're going to have some chemistry there. I didn't tell you about CO1-. We got holmium and erbium and more, and uranium. And you can see the list has just been growing and growing. And I never would have thought any of this was possible based on the traditional beliefs of reductive chemistry in the F element area. So my message to you all is go home and question assumptions. Because I bet in every area of science that's represented in this audience, there's some assumption just as basic as what I've shown you today that is completely wrong. It won't be redox or bond length, it'll be something else. But in every individual research area, I bet there's something basic that's wrong. And if you can push through those assumptions, you'll get all kinds of new science. Now, if you want to think more generally about assumptions, George Whitesides has a paper in Angewandte that talks about assumptions in life. And it's easy for me to say question assumptions, but how do you do that? And I have a quote from the late John Corbett that it's always difficult to predict the unimaginable, right? It would have been difficult for me to predict all of these things. But Whitesides has a prescription for how to do this. He says, start by identifying areas where change would matter in your area of science. And then ask if imaginable science might cause this change. So that's your charge. Go out and think about your area. Go out about thinking about questioning assumptions in that area. And I think you'll be handsomely rewarded for that. None of this would have been possible without a wonderful group of students. And the ones in black have graduated, and the ones in blue are in the group. It took some very special, hardworking, talented students to make this happen. This is a recent group picture of the group huddled around the glove boxes. And I also want to thank my collaborators. In the X-ray, Bob Dodens and Joe Ziller, and the Fricke group for the theory, and the Borvik group for the EPR. We couldn't have done this without all those collaborations. And this was supported by the National Science Foundation and the Chemical Sciences, Geosciences, and Biosciences Division of the Office of Basic Energy Sciences of the Department of Energy. Wanted to say that whole thing in case John is here. And I just want to give a shout out to Joe Ziller at the end, because without Joe Ziller's work to get these crystal structures, you wouldn't have believed anything I told you today, and we would have no story. So Joe, thank you very much for all your work. You made this happen. Thank you very much, and I'd be glad to answer any questions.
You mentioned that most metals bind dinitrogen,
Right.
This amino compound also bind liner fashion. You don't look at steric in there.
Yeah. So the question is, I showed the metallocene that attached to dinitrogen side on. All the other ones do too. So when we made that first one, it was a rare example. Now we have 20 or 30 of these, and it's the signature structure for the lanthanides. So it's not a matter of sterics, I think it's a matter of electrostatics. You have a 2+ anion and 2 3+ metals, and the best way to optimize electrostatics around that is to go side on like that. Orbitals are not particularly important in that system. That's how I would say that. Everybody wants to go to the reception. Dave, except Dave. +4, okay. So this is a really good point. I just told you the story about the lower oxidation states. And in my dreams, what we want to do is look at the higher oxidation states. So I showed you there's only cerium +4, there's a little praseodymium +4, a little terbium +4. But I bet, under the right conditions, you can fill out the row with the +4s. It's a whole different type of chemistry. But we're having so much fun with the reduction side now, we haven't got to the oxidation state. But I was going to write my last NSF proposal on +4, but then we got the single molecule magnets and the new +2 ions, and so I stayed in the reduction side. But you're exactly right. We should question the assumption that there's only a couple of +4 ions. Oh, Ken. Oh.
Oh, Ken. Sorry. I'll shut up.
F.
Since the rare earths aren't as rare, are they cheaper or more expensive than transition metals?
So his question is, since the rare earths are not rare, are they cheaper or more expensive than transition metals? Sort of depends on what transition metals you're talking about. But in the course of, when I started working with rare earths, nobody knew what they were, nobody cared. But in recent years, they've become critical to energy efficient devices. So iron, neodymium, boron is the best magnet you can get. It's in your automobiles, it's in every energy efficient motor, it's in fans, it's in all kinds of things, it's in wind turbines. And so that, there's a reasonable amount of neodymium, but you need a little bit of dysprosium in there to make the magnet better, and there's not so much dysprosium around. And so they've become precious, and we have a mine in California, in Mountain Pass, so if you ever go up to Las Vegas on Highway 15 and you come to the Mountain Pass where you can just see Vegas in the distance, you look over your left shoulder and there's a huge open pit mine where they used to say there's enough lanthanides for 200 years. It's one mountain in the Mojave Desert where it's just intense ore bed, about 7% of lanthanide ore there. But they shut it down because China was producing it cheaper. And so China now has the market for making rare earths, and they're also growing a lot. And so they need all the rare earths they're producing. And so now the rare earths are actually a strategic material because they're used in so many defense-related devices. And you can't blame China for not wanting to sell them because they need all they produce. And now they're bringing the Mountain Pass mine up. And so we should be making it in the States again. So the prices have been going up and down, a lot of speculation. If you're interested, this is a stock question. Yeah, they've been going up and down, but I think because they are unique in what they do for energy-saving devices, they will continue to be precious for demand, not for abundance. And now to Ken.
Is it imaginable to think about shuttling between oxidation states for catalytic ethanol?
So the question is it imaginable to think about shuttling between oxidation states for catalysis? That's a tough one. These are very reducing, and we get there with potassium. So to go back and forth is a little difficult, but I wouldn't want to make an assumption on it.
Other questions? Okay, well, there's a reception. You all know where that is. And let's thank Bill again.